And finally, we come to the bit where we actually calculate the moment arms based on the data we output from the GateSim model. So this is looking at the folder where we stored the model, and the output creates these files all ending in .tab, and you get basically one per object, except for muscles, which actually output two files. You have a strap file, which gives you details about the path that the strap took, and the regular tab file, which gives you the basic details about the muscle, the basic information, and that's what we'll use at. You can open these from inside anything that understands tab delimited format. So Excel is fine, but you can also use, Python or MATLAB or R or whatever your preferred method of analyzing data is. Just for illustration, I'm going to show some stuff in Excel, but probably if you've got a lot of this to do, then one of the more programmatic things would be better. So this is the hip joint data. As you can see, it's tab delimited. It's got column headers, a whole bunch of information. You've got the time in the simulation. You've got the positions of the joint. You've got the forces that are generated. But the bit we're interested in is the joint angle here, which is nicely separated out, and that's what we want. If I then look at the muscle file, this is the iliacus file. Again, we've got information about the muscle. These are values that you set when you define the activation of the muscle. This is the current activation, and it's this column here, which is the length of the contractile element that has the information we want in terms of muscle length that we need for doing tendon travel method. So what we can do now is that we can take this data, create a new spreadsheet. Let's put the length data there. And put the angle data here. And that's the information that we need to do the calculations. If we have a look at this data, in fact, this looks exactly like the data you'd get off a tendon travel experiment. So we've got angle across the bottom, and we've got angle across the bottom, and we've got length in the y-axis. And the gradient of this curve is actually the moment arm. And you can see it's really interesting. This is the extension part of the curve. If you remember, this is 0, and we've got sort of 20 degrees of extension, and then we've got a large amount of flexion. And we can see that the moment arm drops off as flexion increases. And actually, with the way we've modeled this muscle, which may or may not be anatomically correct because we did it quite quickly, we actually get a change from it being a flexor to it being an extensor at the very, very extreme of flexion. And that is something that happens when you get to very extremes. So this is nice. You can treat this exactly as the way you would treat any tendon travel data. You're after the gradient. Experimentally, because this tends to be quite noisy, you often end up doing some smoothing. Either you fit a polynomial and then you differentiate directly from the polynomial, or you might do some sort of spatial filter. In fact, it's probably not necessary for simulation data, because simulation data is generally very clean and there isn't really any noise here. So we simply need to calculate the gradient, which we can do very easily just using the change of length divided by the change of angle. And we can use a very simple formula for that. We can just use the length at time plus 1 minus the length at time minus 1 divided by the angle at time plus 1 minus the angle at time minus 1. And that will give us a sensible value for gradient for moment arm. So it's about sort of 2.5 millimeters, which is not an unreasonable value at that particular angle. And obviously we can calculate this for the whole of the data set. and this will let us see how it changes. Now, the only thing that you have to be a bit careful about with this is that quite often, because the joint is hit at the end of a range, the angle change is very small, and anything divided by a very small number, which might even be 0, is going to give you an unrealistically large number. So there will be a few spikes if you look at the whole of the range, and you might want to do something about that. So if we plot these two together, hopefully this will work. I have a few problems getting the right plot I want out of Excel, but that's right. So you can see the spikes where we've got very small amounts of change. That's not what we want. But if we change the range here, and we've got just sort of sensible options, so that the minimum isn't going to be less than a centimeter, and the maximum isn't going to be more than 2 centimeters, really. So if you ignore the spikes, as I say, there's just values caused because the angle change is tiny at certain parts. You can see exactly as you predict a beautiful change in moment arm, which varies as you change the extension and flexion angle of this particular muscle, calculated directly by tendon travel. So a sort of consistent fashion to experimental data, which is often a very good way of doing these things. So that's it. That's how you can get useful data out of GateSim. It really doesn't take very long once you actually have the anatomical data up front. There's no reason why these sorts of analyses are particularly slow. I generally build the complete muscular model, and then I can do all these analyses together, because there's no reason why you can't output lots and lots of muscle data all at the same time as you move the joint through its full range of motion.